Okay guys, so till now you have learned that when we apply either a tensile load or a compressive load on a body like this, okay, if the initial length is L, definitely under the action of this tensile load it elongate, okay, and if the elongation is delta, in that case we can say that our strain due to this tensile load is simply delta by L, and from this strain we can calculate the stress due to this tensile load, and that is nothing but E times strain. Okay, and now you have also got a concept of shear force and bending moment. In the last two videos, sorry, in last three videos we have discussed a lot how to draw the shear force diagram as well as the bending moment diagram, and there you have learned that if this is a simply supported low beam, okay, and if it is subjected to load, transverse load at a distance of A from both the support, you can definitely draw the shear force diagram, and the shear force diagram looks something like this. Okay, this is positive and this is negative. Okay, if this is A, this is B, okay, and C and D. In between C and D there is no such shear force. Okay, and if you draw the bending moment diagram, it looks something like this. Okay, this is the bending moment diagram, and here you can see that from C to D the bending moment is constant. Okay, so now in this video I will discuss about how to calculate the stress due to bending moment. Got it? We will use the simply this concept, stress due to tensile load, okay, or the stress due to compressive load, and in this case we will have only the bending moment, no shear force. Here you can see that this beam from C to D, here there is no shear force. Okay, the shear force is simply 0, and you have only bending moment, correct, and this case is known as, do you know? Yes, this is known as pure bending. Okay, and we can say that this part from C to D, this is under the action of pure bending. Why? Because in this part there is no shear force. Okay, shear force is 0. Got it? So due to this pure bending, we will calculate the stress on this beam element. So before finding the stress due to this bending moment, we have to make some assumption, and the very first assumption is plane section remain plane. Okay, many of you may heard of this term, this phrase. Well, let me discuss this particular phrase for those who are not familiar. So what does it really mean by this term, plane section remain plane? This means simple, the meaning is simple. Okay, let's say you have a beam like this. This is the front view, and these are the support. And if you take any plane cross section, let's say you have marked some cross section like this. This is one plane, this is another plane. Let's say you have marked this one by using chalk pencil. Okay, now you are simply applying some arbitrary load. It may be anything, it may be some point load, it may be some UDL, it may be some triangular load, anything, it doesn't matter. So definitely due to this loading, what will happen, this beam will bend like this. Agree? This will bend like this. And here if you observe this chalk line, you can see that this line has become this one, or this one, or this one. That means this chalk line has not bent like this or like this. Okay, so this is the meaning that this plane section remain plane, and it make it clear that these edges remain plane like this. Okay, they don't bend or deflect like this. It is not the case. Got it? So this is the meaning of plane section remain plane. Okay, now go back to our case, that is we have a beam element that is under the action of pure shear. Got it? Now we will simply cut a section of length dx and we will analyze everything on that section. So this is the section. Okay, this is the element and the element is under the action of pure bending. There is no such shear force, only bending. Got it? And now after the application of this bending, what will happen? It will bend. Let's say this is the shape after bending. Okay, and we have already discussed that plane section remain plane. That means, by the way, the length is only dx. Okay, this is the length and every fiber has a length of dx. Every fiber has a length of dx. Okay, so now plane section remain plane. That means this face become this one and this face become, yes, this one. So now you can see that these two face due to the curvature has subtend an angle. Okay, and we will define this angle by simply d theta. Got it? And let's say this is the neutral axis. Okay, this is the neutral axis. Now what is neutral axis? I'll discuss in a while. Okay, so this is the neutral axis and from this neutral axis, let's say the center has a distance of r. So this r is known as radius of curvature. Note it, r is radius of curvature. Okay, that means curvature is simply 1 by r. Got it? And by the way, what is neutral axis? Well, let's say this was your beam, this was support and you have applied a load. Okay, and in this case, let's say this is x direction. Okay, and let's say this is y direction. Okay, so this is the 3D shape. Here you can see. So we have y direction marked in color red. This is the y direction. So this is xy plane. Got it? No, this is not xy plane because this is another dimension, that is z. So this is yz plane. So we have xy plane here. This is the xy plane and we are applying the load along this plane. So definitely the beam will bend in the xy plane only. Got it? So due to bending, what will happen? Some fiber, here you can see, some fiber has been contracted. Okay, initially the line was like this. Initially this was the line, this was the face. So here you can see at this top of this line, dotted line, all this fiber has shortened, but below of this dotted line the fiber has been elongated. Okay, so in the meantime, in this middle there is a plane which has neither elongated nor shortened, and this plane is known as neutral surface, and the neutral surface where meet this plane of symmetry of loading is known as neutral axis. Okay, so the first concept is neutral surface, which neither elongated nor shortened. Okay, that is known as neutral surface. And when neutral surface is cut by this xy plane, or the plane along with the load is applied, is known as neutral axis. Got it? Now again come back to this picture. Okay, so here initially all the fiber had a length of dx. Okay, so now consider a fiber at a distance of y. At a distance of y, we are considering a fiber. Okay, so what is the length of this fiber? This is y. Simply, if we have an arc with radius r and angle theta, what is this length of this arc? S is r theta. We will apply the same philosophy. Okay, so for this fiber, what is the radius? Well, for this particular fiber, okay, for this fiber, the radius is r plus y and the subtended angle is d theta. So the length is d theta. And initially, what was the length of this fiber? Initially, the length of all the fiber was dx. So initial length was dx. Okay, and now the only fiber which has the length of dx is the fiber along the neutral axis. That means this fiber, okay, dx, and this is nothing but r times d theta. Agree? So now what is this length? What is the present length of this yellow fiber? It is coming as r times d theta plus y times d theta. So what is the increment of this length? What is the increment? The delta is nothing but y d theta. That's it. Because initially the length was r d theta and now the length is r d theta plus y d theta. So the delta is y d theta. Okay, and strain is nothing but delta by L. You know that this equation, the very basic equation. So delta is coming as y d theta and you had L as r d theta. L means original length, that is dx, that is r d theta, and you are getting strain as cancel d theta y by r. Okay, so you have now strain, and you know stress is nothing but modulus of elasticity times strain. So stress is coming as E times y by r. So you have got the stress due to this bending moment. Okay, but here you can see that in this equation bending moment is missing. Bending moment is missing. Okay, so we will try to derive another equation where we can express this stress in terms of bending moment m, because here you know the bending moment m, that is PA. So if you know the bending moment, simply you can calculate the stress. Okay, so let's say this is our equation 1. Okay, now we will derive another equation. So let's consider the beam again. Okay, so in this beam, in this part of the beam, this is the part from here. Okay, and here the bending moment is acting as m. Okay, and now you have got that along the cross section. If we look at the cross section, let's say the cross section is this one. We don't know exact cross section, maybe anything. Okay, so this is the cross section. So you can see that along the depth of this cross section, the stress varies like this. The stress varies linearly if this is the neutral axis. Okay, and y is the distance from neutral axis. So from at center it is 0, because at center y is 0, at center y is 0, so stress is 0. Okay, but at a distance of, let's say this is your distance of top fiber from center, and it is, let's say, yt, and this is, let's say, the distance of bottom fiber from center, so this is, let's say, yb. Okay, so here the stress is coming as sigma is equal to E times yt by r. This is the stress, and it is compressive in nature because the bending is like this. So all the fibers in the concave side or in this side are in compression, okay, and all the fiber at the bottom of this neutral axis are in tension. Okay, so I am marking all the fiber in tension in red color and all the fibers in compression in yellow color. So you have got an idea about the compression and tension state of the fibers. Okay, so here you can see these are all compressive stress varying linearly. This is compressive, and all the stress below the neutral axis are tension. Okay, so now consider the cross section again. Okay, so we are considering the cross section now in a large amount. Okay, this is the neutral axis. Now let's consider any element at a distance of y from neutral axis. So let's say this is the element with cross section of only delta A or dA. Okay, so what is the stress here in this element, in this area? You can find it. So the stress here is simply E times y. Y is the distance from neutral axis divided by r. Any problem? No. Okay, so what is the total force acting on this element? So simply the force acting is stress time area, which gives us E times y by r. Okay, so this is delta force is coming as this one. Now what is the moment about this neutral axis? Okay, due to this force or the force acting on this element, okay, you can simply calculate the moment by multiplying df with this distance y. Okay, this gives you E times y by r times dA times y. Okay, now if we integrate this moment for this whole section, it should be equate with this external moment m, because there is no other moment. So this internal moment must be equate with this one. So dm, integral of dm is coming as your moment m, and this is equals with integration of E by r time y square dA, and if we take out E by r, we have an equation, famous equation, that is y square times dA. Integration of this term is known as, yes, moment of inertia. And if we express this moment of inertia by this term I, we have a very beautiful equation here. So now we have this formula. Okay, that is moment is equal with E by r times I. That's it. Okay, but still here you can see the stress is not expressed in terms of moment. That was our aim. So again erase everything. Here you can see that initially we have an equation which says that stress is E by r times y. So from here we can say that E by r is stress by y. or stress can be also expressed as F. Both are same. Instead of sigma we are using F. Why? I am telling you. Okay. And in this equation also you can say that E by R is M by I. Okay. So if we combine now, we can say that M by I is equals with F by Y is equals with E by R. So using this equation, a group of equation, you can find out anything, any variable. Okay, whether it is stress in terms of moment, whether it is the distance of fiber in terms of all other things, or whether it is the curvature. Okay, and to remember this formula, this is $1 million equation. To remember this very basic equation, you can follow my rule. That is, though it is not my rule actually, it is a very popular phrase, that is, may I follow you, Elizabeth Rani. Got it? That's it.